So before watching this presentation, hopefully you had a chance to read through the Jones and Kotler chapter that I assigned for you to read. So essentially, they discuss how to read both qualitative and quantitative research. We'll cover qualitative research in a few weeks, but the main part that I'm going to focus on, and we're focusing on this week, is quantitative research. And so that's what I'm going to discuss here. So essentially, learning quantitative statistical techniques is mostly outside the boundaries of this course, but I want you to at least know enough to be dangerous, which is, made me think of Top Gun, whatever. Anyways, I'm going to break up my presentation about quantitative statistics into descriptive statistics and inferential statistics. So if you feel like you already know what descriptive statistics are, so basically the ideas of central tendency, variability, and shape, which were also discussed in Jones and Kotler, then you can skip over this presentation and just watch the inferential one. So this is mostly for people who don't really have a strong background in statistics, and hopefully this will help you to be able to develop some basic skills around reporting descriptive statistics when you're doing your own research, and also reading and understanding them in published literature. So first of all, what are descriptive statistics? Essentially, the book definition would be the application of statistical techniques to summarize and make sense of a particular set of data. These are around quantitative data. There are two kinds of descriptive statistics. Univariate statistics, which we'll talk about first, and as the idea of univariate suggests, univariate statistics describe or summarize just one variable. And then bivariate statistics describe or summarize the relationship between or comparisons between two variables. So those are the two main categories of descriptive statistics, univariate and bivariate. So univariate statistics there are three basic characteristics of a univariate or a single variable statistic. So the idea of central tendency, variability, and shape. And so I'm going to go all through the specific statistics that are captured by these three constructs in this presentation. And univariate statistics, let's connect back to our research questions and really what we're interested in finding out. So these don't stand alone in a vacuum. You should be using descriptive statistics to answer descriptive quantitative research questions that are univariate in nature. So what's some examples of those kinds of research questions? So first of all, let's say we wanted to know, what are ASU students' opinions about the availability of academic support services on campus? So the single variable that we're interested in here are opinions of academic support services. Maybe we'll measure it in a couple of different ways. Maybe we'll ask about tutoring. Maybe we'll ask about what else? Technology, several different dimensions on that. But really what we're interested in are just one overall variable, the idea of academic support services. We're not looking at relationships among variables, right? Just one variable. So that's a descriptive research question that's univariate in nature. Another one might be, how frequently do ASU students use tutoring services? So we could answer that with the response to asking students or watching students come into tutoring and measuring maybe the number of minutes they spend in tutoring services, or do a survey about how frequently they report using tutoring services. But again, the response to that would be one variable, right? So the frequency of use of tutoring services, and we wouldn't be looking at any relationships or anything like that. So we could answer it with univariate statistics. And then finally, maybe we could ask, to what extent do faculty use technology in the classroom? So again, we could survey faculty or maybe observe faculty and measure, using quantitative data, the frequency to which they're using technology. And then we could use univariate statistics to respond to a research question. So I'm going to go through specifically the different types of univariate statistics next, and then we'll return to an example of a research question with actual data to use to respond to that research question with univariate statistics. So central tendency, measures of central tendency, hopefully this rings a bell. Hopefully you have some sort of minor knowledge of statistics, and the three major measures of central tendency, which are basically numerical values that help us consider the typical nature of our quantitative variable. Hopefully these are familiar to you. So first of all, the mean. So essentially that's just the arithmetic average of any data set. So 3 is the average of 2, 3, 3, and 4. That's the average. You can compute the average, right? The median is another measure of central tendency, and it's essentially the center point of your data. So basically what you do is you put all of your numbers in ascending or descending order, and then you go through and you figure out where exactly the center number is. So right here in this example of this data set, let's say we have 1, 1, 3, 4, and 9. So note they're in ascending order. And then we see that right in the middle here is 3, right? So that's what the median is. If let's say we had an average, or an even number of numbers in our data set, then you would just go through and find the two middle numbers and then find the average of those two. So in this data set, 1, 2, 3, 4, and 7, 1, 2, 3, and 7, there are only 4 numbers, and so we go to the middle, our middle two numbers, 2 and 3, and the average of 2 and 3 is 2.5. So 2.5 would be the median of our data set. So it helps us find the middle of our data set. And then the mode is essentially just the most frequently occurring number in our data set. So let's say we had a data set of 1, 2, 3, 4, 4, and 5. 4 happens twice in our data set, so it's the most frequent number, so it's our mode, the most often. So I'm going to give you a few examples of these measures of central tendency in practice. So in some cases, the mean can be a misleading and or incomplete measure of central tendency. So income is a really good example of this. In this slide, we plot out the mean and the median family incomes in the United States between 1947 and 2004. So as you can see, the mean income, the hot pink line, is consistently higher than the median line, right? That's because the average is pulled up by what we call outliers. So the richest people have a great deal more income proportional to the poorest people, which pulls the mean upward. But the median, the measure of a median is referred to as a resistant statistic because it's less susceptible to extreme values. So this graph helps us to understand and see that from the end of World War II until the late 1960s, the rich-poor divide was pretty remarkably stable, and it even narrowed over long stretches. But then this started to come apart around 1970, and you can see by eyeballing the trend in mean and median family incomes, if everybody's family income had grown at the same rate, that those two lines would be moving in lockstep parallel to one another. But when the top half grows faster or falls more slowly than the bottom half, then the mean is pulling away from the median. And so this is sort of, there are a lot of explanations for why this huge gap between the mean and median income is seen today. A lot of it is perhaps attributable to the enormous income gains in the top 1% of earners in the United States. So, for instance, you know, CEOs and sports and entertainment superstars and whatnot, and Bill Gates. So that those top earners have really skewed the mean income in this country a lot higher than what the median income is. So in this case, reporting both mean and median gives us a lot of information about the distribution of income in our society and how that trend has changed over time. Mode is also another helpful measure of central tendency that really helps us to understand data that maybe don't take a totally normal distribution. So this example up here of law school graduate starting salaries gives us a good instance of where mode is helpful. So in this case, the mean salary of a law school graduate in 2009, full-time, that is full-time, they don't include part-time employees in this, is $93,000, and the adjusted mean, which is actually the median in this case, is about $85,000. But by only reporting those two measures, we overlook the fact that there's a large number of law school graduates who graduate and make over $150,000, right? See that peak over on the right side of the graph? But then there's also several high peaks quite a bit below the mean, around maybe 30,000 to 70,000. And so really what this graph tells us is that people who are graduating from law school, there's a group of maybe haves or winners in the law school salary sweepstakes, probably those from the most elite law schools, right, who go to work for big white-collar corporate firms or what have you that are making a ton of money. But then we also have a large group of law school graduates who are making a very low starting salary, probably not even enough to cover their law school tuition. So the mode is helpful in this case to help us understand that there really isn't just sort of a lot of people right in the middle of this data set, but instead there are more frequently people at sort of like the two polar ends of the data set. Another univariate statistic that's typically reported in descriptive research are measures of variability or dispersion. Essentially, those are ways to measure how much a set of data points differ from one another. So dispersion is important in addition to measures of central tendency, because as even the examples I gave you in the prior slides indicated, using just central tendency alone can be misleading. So sometimes it can give incomplete information and make either things look better than they are or worse than they actually are. And so variability and dispersion are additional ways that we can get a sense of the true nature of the phenomenon we're interested in studying. Okay, so one of the first measures of variability that people think of is range. Essentially, that's the difference between the highest and the lowest numbers in your data set. It's a very crude measure of variability, however, and it's not commonly used. The reason is that there are oftentimes outliers in your data set that make the range sort of difficult to make sense of. So a good example, again, is household income. So here is the distribution of household income in 2010, and you can see it ranges from 0 to over 250 million. So in this case, we don't exactly know what the largest household income is, but we could assume it's probably maybe the household of Bill Gates, who made $7.8 billion in 2010. So our range of household incomes is about $7.8 billion, all the way from an amount near 0 probably to 7.8 billion. So because of the outliers at the top end of our distribution, that range is a pretty difficult measure to make sense of, right? Sometimes used instead of range is what's called intraquartile range, and this helps to attend a little bit better for outliers. Essentially what the intraquartile range does is split our data set into 4 groups. And so the interval from the first quartile to the third quartile contains the middle 50% of the data. And then the interquartile range is the length of that interval. So in this case, our interquartile range would be about $65,000. And this tells us that the more stable part of the income scale, the range or the interval between $25,000 and $90,000, which captures 50% middle of our data, is a really more representative range of household incomes in the United States. So it's not as influenced by extreme data values. And again, getting back to the idea that median is a resistant statistic, so is interquartile range. So it's typically used as a measure of spread, especially for skewed distributions, stuff like income, because it isn't influenced by sort of these outrageous outliers like Bill Gates' income. Okay, so the most common univariate statistic that represents variability is the standard deviation. So in most of the quantitative research you'll encounter, standard deviation will be the preferred statistic that's reported. Essentially, the standard deviation is a function of the distance between any given case and its mean, adjusted for the size of the sample. But what's important for you to know is this idea of the 68, 95, 99.7 rule. Essentially, I'll give you an example on the next slide of this, but that means that about 68% of the cases in your data set will fall between 1 or less than 1 standard deviations of the mean. About 95% of the cases in your data set will fall within plus or minus 2 standard deviations of the mean, and about 99.7% of cases will fall within plus or minus 3 standard deviations of the mean. So when you're getting, if you observe a case that has a pretty high standard deviation, that indicates that it's pretty far away from the mean, and it's a pretty extreme case. Let me show you on the next slide how to really understand that rule. So on this slide, I have a table that summarizes the data for the ACT tests between 2009 and 2011, and it really helps to illustrate how useful standard deviation can be. So first of all, seeing up here that the 4 main test sections as well as the ACT composite results are reported for both the mean and the standard deviation. So first of all, which of the main sections of the ACT, the English, math, reading, or science, has the most dispersion? So if you look at the if you look at the standard deviations, you can see that English has the highest one, right? 6.4. So essentially that means that English, students who took the English test, their scores were more all over the map and sort of all over the range of possible scores compared to maybe science, where the standard deviation was only 5.1. There's certainly still variation. Everyone didn't get the exact same score, right? There's variability there, but there was more variability comparatively in the English test than the science test and the math test. And using that 68%, 95, 99% rule, applying that to these data, so we can look at the English test and say, all right, so given that the standard deviation was 6.4 and the mean was 20.6, we know that about 68% of students will score within plus or minus 1 standard deviation of the mean. So calculating that out with the data using the 6.4 standard deviation, 6.4 plus 20.6 is 27, and 20.6 minus 6.4 is 14.2. So we can say that about 68% of students will score between a 14.2 and a 27 on the English section of the ACT. Okay, so the final characteristic, descriptive characteristic of a univariate statistic is thinking about its shape. And the technical term for describing the shape of a univariate distribution is with a frequency distribution. Essentially, that's either a table or a graph that gives us a visual understanding of the data and shows the frequency of each unique data value. And I'm going to give you some examples on the next slide. Okay, so first of all, tables and polygons. So I again use income as my example because those data are really easy to get and you can do a lot of nice things with income data. But anyway, so on the left side is a frequency table that illustrates individual income in 2008. So as you can see, note how I grouped income on the left side into a range according to every $5,000. So it's obviously, we can't do a table with every single value of income because when you're using a variable that's on a continuous or interval scale, that gets unbelievably unwieldy. And so oftentimes people will group their frequency distribution tables into intervals and show the frequency of each interval. The frequency polygon, which is the line graph on the right side, oftentimes that helps to clarify trends better than do tables or most other graphs. So essentially, this visually shows us the proportion of individuals who have incomes above around 70,000 is where the line flattens. So it shows us that most of the population has incomes that are below around 70,000. Really, frequency polygons help to show both the behavior and the distribution of a variable. It's just translating these data that are in this table into a visual form. Even more common are histograms and bar charts, right? So the difference between a histogram and a bar chart is just that histograms, one of which is on the left side, use ordinal data, and then bar charts, which is on the right side, use nominal data, right? So you just do the frequency of your variable on the Y scale, and then your data are on the X scale. So essentially one example, so again, I used a histogram of individual income data. So those data have an order, so that's a histogram. But then the second bar chart down here groups income according to demographic subgroups. So all people, men, women, white, black, Asian, Hispanic. So because those are nominal variables, right? There's no order to them. We used a bar chart to display those data. Okay, so when we go to describe the shape of our distributions, this is important because it helps us to understand what kinds of statistics we should use. And so a symmetric distribution is one just like illustrated up here on this screen, this figure up here, all three of those or all four of those, are symmetric distributions. Essentially, that's when two halves of the distribution mirror one another, right? And so we can see that in this picture, the spread is different, right? So the variation is different, but the measures of central tendency are all the same, right? So the mean and the median and the mode are all the same. So when your data take the distribution that is symmetric in shape, you would best probably use the mean to describe it. So the mean is the same as the median, is the same as the mode, so you can just use the mean in this kind of case. So skewed distributions are those that do not take on a symmetric appearance. Essentially, it's when scores with the highest frequency do not fall close to the mean. And so skewed distributions can either be positively skewed, which means that the most frequent scores are low, or they can be negatively skewed, and so that means that the most frequent scores are high. And I'll show you an example on the next slide. But essentially what's important to know is that in a skewed distribution, the central tendency measures will not be equal. And in some cases, when the distribution is positively skewed, the mode will be less than the median will be less than the mean, and when the distribution is negatively skewed, the mode will be the greatest number, followed by the median and the mean. And so in skewed distributions, it's most appropriate to report the median as opposed to the mean and the mode. You can report all three of those, but really what you should focus on to discuss is the median, the middle of the data, for a skewed distribution. Okay, so this example, again, drawing from my favorite, income, illustrates a graph or a set of data that is positively skewed. The shape of this frequency distribution takes on a positive skew. So essentially, again, positive skews means that the most frequent scores are low and the tail is towards the high scores, right? You can see that. If it was the reverse, if it was a negative skew, the most frequent scores would all be high, and the tail would be towards the low scores. But this is positive skew. Household income in the United States is a positively skewed distribution. So the mean is to the right of the median, right? Correct? And where's the mode? The mode is at the left side of the data, right? So the mode is over to the left, and the median is in the middle, and then the mean is to the right of the median. That's what happens when you have a positively skewed distribution. Okay, so the final term that we use to describe a univariate distribution is kurtosis, and that essentially gets at the peakedness in a curve and the thickness of its tails. So as you can see up here, we have several different symmetric frequency distributions data up there, but there are different levels of peakedness and flatness in those different distributions. So essentially, I don't want to get too technical with you. I just wanted you to be aware that this idea of kurtosis describes the relative peak of the data, and something like the blue bell curve up there is what we call leptokurtic. So that's when there's high peaks, and then something that's platykurtic is something that's very flat with no peaks, a very low peak, and that's like the yellow curve. So, and then mesokurtic is a normal bell curve. Basically, the kurtosis value would be 0. I sort of feel like I'm getting a little too technical with this, so I'm just going to leave it at that. The idea of kurtosis, just know that gets at the peak of your curve. All right, so let me give you an example of how I would go about reporting the results of a descriptive research question and helping you to think about what statistics you should report when you're writing off your results. So essentially the important thing is you want to comprehensively answer your research question. So let's say my research question is back to what are ASU students' opinions about the availability of academic support services on campus? So let's say I just did a survey with a bunch of different questions asking about students' levels of satisfaction. So one way you could report your results would be, let's say here's the results to one of my questions. Maybe I asked 10 different questions, but here's one of them. I just asked about their overall satisfaction with the availability of academic support services. And maybe, here's what we see. Here's a frequency distribution of their responses to that question. So I could either report it in tabular form, right? Or I could do maybe a nice little histogram and show the results in graphic form, which I think a lot of audiences respond well to. Or we could calculate out the mean, median, mode, and standard deviation, right? So to do that, basically what you would do you would assign a value, an ordinal value to each of your response options here. So very dissatisfied, dissatisfied, neutral, satisfied, and very satisfied. As you can see in the middle, let's say I put them on a scale from 1 to 5, with 5 being very satisfied and 1 being very dissatisfied. All you do then is you multiply your number of responses times that value. You get a weighted sum. You then add up all of your results, get a weighted sum, and then adjust that and divide it by your overall number of respondents to come up with your mean. So in this case, the mean on a scale of 1 to 5 would be 3.27. What would be important if you're reporting the mean is to make sure that your readers know the scale, because I could have made the scale in reverse, right? I could have made very satisfied maybe 1 and very dissatisfied 5, and that would change how I reported the mean as well as the interpretation of that mean. So you need to be careful to be very clear with your readers when you're using ordinal scales, what those scales are, because that affects how you interpret the mean, as well as the median and the mode. So here, if we were going to calculate the median, right, that's the middle of the data, where 50% of the data are above and below, that would be a 3. So if you look up here at my table of responses, you can see that 3 is where the cut point, where 50% of the data are above and below it. And then the mode, again, is the most common response, right? And we can see that the most common response was satisfied. And so the mode would be 4. In terms of calculating the range, you then go to your scale, right? And the difference between the highest value on your scale and your lowest value is from 1 to 5, so your range is 4. And then you can also calculate through your standard deviation, which is a function of your mean squared and then adjusted by your sample size. In this case, I calculated it, and it was 0.479. So that indicates, right, that most of our data, 67%, is between 68%, is between plus or minus 1 standard deviation of our mean. If we go up here to our mean, so 3.27 plus 0.48, so that's about 68% of our respondents fell between a response of 2.8, right, or 2.7, and about 3.8. So if I was going to be reporting the results of this to a reader on campus or something like that, I would comprehensively include both the univariate statistics as well as the frequency graph of the results. People respond sometimes better to visual data, and some people respond better to numeric data. So usually when you're doing a descriptive research analysis, you should include both sort of graphic as well as numeric summaries of your just univariate statistics. So moving on to bivariate statistics. So these statistics describe relationships between two variables, right? Either comparing or looking at the relationships with. Measures of association is how Jones and Kotler referred to bivariate distributions and bivariate statistics. So there can be two major ways that you analyze bivariate relationships. If you're using nominal and categorical data, you use tables. So the two-dimensional tables looking at two variables together are also called crosstabs or cross-tabulations. And then if you're looking at interval and ratio data, you'll use scatter plots or correlations. And I'm going to give you an example of both crosstabs, which use nominal and categorical data, as well as scatter plots and correlations. So in this example, I give you a cross-tabulation that looks at gender and ethnicity for respondents to the National Education Longitudinal Study. Essentially, let's say the research question that we could perhaps respond to in this example is, are there differences in the race of respondents according to their gender? And so again, back to our scale issue. So both gender and race are nominal data, right? So even though up here you can see on the table in the data set they assign numbers to both gender and to race, those numbers have absolutely no meaning. So if we try to calculate the mean in these data, it would make no sense, right? Like the mean race, what does that even tell us? Because it just tells us nothing, because there's no order to our responses. So in these kinds of cases, when we have nominal data and we're comparing nominal groups to one another, we create usually a cross-tabulation table right here, like you can see. So we basically split the data set into the respondents that fall into all of the male by race categories and then the female by race categories. And then we just have the total of each row and the total of each column at the ends. So that is what you would do when your data are nominal in nature. If you're comparing groups to one another on two nominal variables, you can't calculate a statistic or even a correlation or even a mean or a median. Those statistics don't make sense, right, for things like gender and ethnicity. So you have to report it in the form of either a frequency table or a cross-tabulation if you're looking at two variables. Okay, so most of the time when you're looking at bivariate relationships, either for ordinally scaled variables, interval scales, or ratio scales, what you'll see reported is what's called a correlation coefficient. And essentially a correlation coefficient tells us how the values for one variable are associated with or related to those on another variable. So they both tell us the strength as well as the direction of a linear relationship or the association between two variables. And graphically, you can display correlations in the form of scatter plots. So some examples of scatter plots are seen up above. So basically, there are three ways any two things can be related. So think about reading and math. So if there was a positive correlation between reading and math, that would suggest that kids who had low scores on math also had low scores on reading, and kids with high scores in math also had high scores in reading, right? A positive correlation means the two variables move together in the same direction. And so that would be the example of the little scatter plot up on the top left that says 1.0. So that's a positive correlation, a positive relationship between two variables. A negative relationship would be the scatter plot on the very right end of the slide that says negative 1.0 above it. Essentially a negative correlation, thinking of the math example and English example, that would mean that kids who have high math scores have low reading scores, and vice versa. So if you get a high score in reading, you're going to get a low score on math. That means there's a negative correlation. But then there can also be no correlation. That basically means there would be no relationship between math and reading. And that would be the cloud up here on the scatter plot in the middle where there's a 0. So a 0 means there's no correlation, no relationship between two different variables. It's important when we're talking about correlation is that there's no direction that's indicated by that association. So we can't say that somebody who gets a high score or a good score in math causes them to get a good score in reading, or a good score in reading causes someone to get a good score in math. All we can do is say that they're associated or they're not associated. So in terms of the correlation statistic itself, that's called the correlation coefficient, and in statistics it's represented by the letter R. But essentially, the correlation statistic can range between +1 and -1. So as I showed you on the graph or the scatter plots on the prior slide, a really strong positive relationship has a correlation coefficient of +1, and a perfectly negative correlation has a coefficient of -1, and then 0 means there's no relationship. So in terms of a general rule of thumb for interpreting correlation coefficients, usually those that are less than 0.35 indicate that there's little relationship. Between 0.35 and 0.75 are pretty decent relationships, and when two variables are correlated at above a level of 0.75 or -0.75, that's very useful in terms of saying there's a strong relationship between two variables. So that's kind of the basic standard that statisticians use. It's actually put forward by the statistician named Arthur Cohen, I believe, is the first one who came up with this metric. Another important thing to just know is that you might see something that's called R squared, which is basically just the correlation squared. And that is interpreted as a percentage. Essentially, it just helps us to understand the percentage of the relationship or the variation in one variable that can be accounted for by the other variable. That's just a basic statistic that I want you to be aware of, but right now don't get too worried about it. Correlation is really the important thing to know is that it can be between -1 and +1, and a 0 means there's no relationship between two variables. I can teach you how to calculate correlation by hand if you want, but I don't want to spend too much time doing it because there are a lot of programs out there that will just calculate it for you. So one of the programs is SPSS, and up here is a correlation table that shows I calculated the correlation between the SAT verbal score and the SAT math score. So what kind of research question would I be looking at if I'm examining the correlation between SAT verbal and SAT math? So you could ask, was there a relationship between SAT verbal and SAT math scores for college freshmen in 1998? Because those are my data right here. So was there a relationship between SAT verbal and SAT math? So what this table tells us is if we look in here, I know this is kind of annoying, but you look right in here and the correlation that was calculated here is 0.570. So basically that tells us that there is a moderate relationship between a moderate positive relationship, between SAT verbal and SAT math. So a positive relationship between SAT verbal and SAT math. That tells us if somebody gets a high score on verbal, they'll likely get a high score in math, and vice versa. If they get a low score on verbal, they'll get a low score in math. Okay, so this presentation was definitely a very quick and dirty overview of descriptive statistics that are used in educational research. So a few main things to keep in mind is that you can either use descriptive statistics or you can use, descriptive statistics that are either univariate in nature, so one variable, right, or bivariate, so that explain the relationship between two variables. And really what matters and what's important is that you should let your research questions guide what you're reporting. You need to be attentive to reporting comprehensively what your results are, and so also be careful that you're not just reporting means. In some cases, modes or medians will be more helpful, and it's important also to capture the variance and variability in your data. So a final note, and I've mentioned this several times throughout this presentation, is that researchers usually don't calculate these statistics by hand. So they have, a data set either in Excel or in SPSS or in some other statistical program that allows them to run these statistics and not even have to do them by hand. And you can get immediately, on a data set of 10,000 cases, immediately you can calculate means, medians, no problems. I, again, unfortunately, teaching you how to use SPSS is outside the boundaries of this class, but it's important to know that that is an option out there, and you can certainly take other courses at ASU in learning how to use some of these programs if it's something that's really interesting to you. So please let me know if you're interested in further information on learning some of these programs to better help you learn how to do quantitative research, because they're essential now in this day and age because of the size of data sets and the time that it takes to calculate these statistics. It's essential to know how to use these. And again, the final note that I want to leave you with is that the statistics you use should be guided by your research questions. So a lot of times people and researchers will run all these fancy, really complex analyses, but it's useless if it's really not connecting back to the topic that you're focusing on in your research and the questions that you're studying. So that's really kind of the main takeaway from this presentation. Again, I'm happy to answer any question you might have about descriptive statistics in class. And the next presentation about understanding and analyzing quantitative data will be inferential statistics. So that helps us to be able to make inferences from our sample about a population. So that's what inferential statistics are, and those will be the focus of the next presentation.